We've been searching for alien life in distant star systems for decades, spending billions on telescopes pointed at the cosmic horizon. But what if we've been looking in the wrong place? What if the evidence isn't light years away, but right here, hiding in our own backyard? The solar system isn't empty space punctuated by a few dead rocks. It's a collection of worlds far stranger than most people realize. Moons with subsurface oceans twice the volume of Earth's. Atmospheres thick with organic chemistry. Geological activity that shouldn't exist. And in some cases, conditions that mirror the environments where life first emerged on our own planet. Mars gets most of the attention, and for good reason. Rovers crawl across its surface, drilling into ancient lakebeds, analyzing soil chemistry, searching for biosignatures in rock layers that formed when the planet still had rivers. But Mars is just the beginning. Beneath the ice shells of distant moons, in the upper clouds of gas giants, even in the frozen reaches beyond Neptune, there are places where the building blocks of life not only exist but thrive under conditions we're only beginning to understand. The question isn't whether these places could support life. The question is whether they already do. Start with Europa, one of Jupiter's largest moons. From a distance, it looks like a cracked marble, its surface a maze of dark lines cutting through brilliant white ice. Those cracks aren't random. They're stress fractures, evidence of something moving beneath the frozen shell. That something is an ocean, liquid water kept warm by tidal forces as Jupiter's gravity kneads the moon's interior like dough. The ice above is estimated to be 15 to 25 kilometers thick. Below that lies a global ocean potentially 100 kilometers deep, containing more water than all of Earth's oceans combined. Water alone isn't enough. Life needs energy, and Europa has it. The same tidal heating that keeps the ocean liquid also drives hydrothermal activity on the seafloor. On Earth, hydrothermal vents are oases of life in the deep ocean, supporting entire ecosystems independent of sunlight. Microbes feed on chemical energy released by the vents. Larger organisms feed on the microbes. The entire food chain exists in permanent darkness, sustained by geology rather than photosynthesis. If similar vents exist on Europa's ocean floor, and there's every reason to believe they do, then the conditions for life aren't just present. They're nearly identical to the environments where life likely began on Earth. But there's a problem. That ice shell. It's not a thin layer we can drill through with current technology. It's kilometers of frozen barrier between us and any potential biosphere below. We can't see through it. We can't sample it directly. Everything we know about Europa's ocean comes from indirect measurements, magnetic field data, surface composition analysis, and computer models. Yet the ice itself might hold answers. Europa's surface shows signs of recent geological activity, areas where the ice has cracked, shifted, and in some places, material from below appears to have reached the surface. If ocean water has made it up through those cracks, even in small amounts, then pieces of Europa's hidden biosphere might be frozen right there on the surface, waiting to be analyzed. NASA's Europa Clipper mission, launching soon, won't land on the surface. Instead, it'll make dozens of close flybys, using instruments to analyze the composition of ice particles ejected from the moon's surface, map the ice shell's thickness, and search for active plumes of water vapor erupting from cracks. If those plumes exist, the spacecraft could fly directly through them, sampling ocean material without ever touching down. The possibility isn't hypothetical. We've already seen this happen elsewhere. Enceladus, a small moon of Saturn, shouldn't be geologically active. It's tiny, barely 500 kilometers across, and that far from the Sun, it should be a frozen, dead world. But in 2005, the Cassini spacecraft detected something unexpected: massive plumes of water vapor erupting from cracks near the Moon's south pole, shooting hundreds of kilometers into space. These weren't occasional events. They were continuous geysers, proof that beneath Enceladus's icy exterior lies another subsurface ocean. Cassini flew through those plumes multiple times, analyzing their composition. The results were striking. Water, obviously, but also organic molecules. Methane, molecular hydrogen, salt, silica particles that could only come from hydrothermal activity on the ocean floor. Everything you'd expect from an environment capable of supporting microbial life. The presence of molecular hydrogen is particularly significant. On Earth, certain microbes use hydrogen as an energy source through a process called methanogenesis, converting hydrogen in carbon dioxide into methane. Enceladus's plumes contain both hydrogen and methane. The hydrogen is almost certainly being produced by chemical reactions between water and hot rock on the ocean floor. The methane could be a byproduct of geological processes, or it could be biological in origin. We don't know. Not yet. But the fact that we can sample material directly from Enceladus's ocean without landing, without drilling, without even entering orbit, makes it one of the most accessible places in the solar system to search for extraterrestrial life. Then there's Titan, Saturn's largest moon and the only moon in the solar system with a thick atmosphere. Stand on Titan's surface and you'd experience air pressure similar to Earth's, though you'd need a pressure suit anyway because the temperature sits at -179 degrees Celsius. The atmosphere is mostly nitrogen, like Earth's, but with methane mixed in. That methane drives a weather cycle eerily similar to the water cycle on Earth. Methane evaporates from lakes, forms clouds, falls as rain, carves river channels, and pools into seas. Titan has lakes. Not water, obviously, but liquid methane and ethane, hundreds of them dotting the polar regions. Some are small ponds. Others are the size of Earth's Great Lakes. Radar imaging from the Cassini mission revealed coastlines, islands, and river deltas. One body, Kraken Mare, is larger than the Caspian Sea. Life as we know it can't exist in liquid methane. It's too cold, the chemistry is wrong, and water-based biochemistry simply doesn't function at those temperatures. But life as we don't know it? That's a different question. Scientists have proposed theoretical biochemistries based on methane instead of water, using different molecular structures and different chemical reactions. It's speculative, but Titan offers a natural laboratory to test whether such life is even possible. More likely, though, is that if Titan harbors life, it's not in the surface lakes. Like Europa and Enceladus, Titan is believed to have a subsurface ocean of liquid water, buried deep beneath its icy crust. Data from Cassini suggests this ocean might be in contact with a rocky seafloor, providing the same potential for hydrothermal chemistry that makes Europa and Enceladus so promising. What makes Titan unique is the complexity of its surface chemistry. The atmosphere is a factory of organic molecules, constantly producing compounds that rain down onto the surface and accumulate in layers. Over billions of years, this process has created a surface rich in the raw materials of life, a prebiotic chemistry set on a planetary scale. If that material ever reaches the subsurface ocean through cracks or impacts, it could provide an additional source of organic nutrients for any potential biosphere below. These aren't the only candidates. Ganymede, another of Jupiter's moons and the largest moon in the solar system, also has a subsurface ocean. Callisto might have one too. Even distant Pluto, reclassified as a dwarf planet but no less interesting, shows signs of a liquid water layer beneath its frozen nitrogen surface. The pattern is clear. Subsurface oceans aren't rare in the outer solar system. They're common. And wherever liquid water exists in contact with rock and energy sources, the potential for life exists. But let's zoom back in, closer to home. Mars might not have subsurface oceans, but it has something else, a history. Billions of years ago, Mars wasn't the cold, dry desert we see today. It had rivers, lakes, possibly even a northern ocean. The atmosphere was thicker. The climate was warmer. Liquid water flowed across the surface for millions, maybe hundreds of millions of years. Long enough for life to emerge, if the conditions were right. Then something changed. Mars lost its magnetic field, leaving its atmosphere exposed to solar wind. Over time, the atmosphere was stripped away. The water either escaped into space or froze into the soil. The surface became uninhabitable. But life, if it existed, might not have disappeared entirely. On Earth, microbes live kilometers beneath the surface, in groundwater, in cracks in the bedrock, surviving on chemical energy in total darkness. If Martian life ever existed, it could have retreated underground as the surface became hostile, persisting in subsurface aquifers or pockets of liquid water trapped in the soil. We found evidence of liquid water on Mars, not on the surface, but beneath it. Radar data from the Mars Express orbiter detected what appears to be a lake of liquid water buried under the southern polar ice cap, kept liquid by pressure and dissolved salts. If confirmed, it would be the first known body of liquid water currently existing on Mars. The implications are obvious. If there's liquid water, there's potential habitat. And if there's habitat, we need to look. Looking for life underground means drilling. On Earth, that's routine. On Mars, it's an engineering nightmare. The farthest we've drilled on another world is about 7 centimeters, barely scratching the surface. Reaching subsurface water on Mars would require drilling hundreds of meters, possibly kilometers, through frozen soil and rock in temperatures that average -60 degrees Celsius. The drill bits would need to withstand extreme cold, operate autonomously without real-time human control, and avoid contaminating the very environment we're trying to study. It's not impossible, but it's not happening soon. Which brings us to the surface. If we can't go deep, we go wide. Mars rovers have been searching for signs of ancient life in the rocks, looking for biosignatures, chemical or structural evidence that life once existed. The challenge is that Mars has spent billions of years erasing its own history. Wind, radiation, and chemical weathering have degraded organic molecules. Even if life existed, its traces might be too faint to detect with current instruments. But there's a workaround. Certain environments preserve biosignatures better than others. Ancient lake beds, hydrothermal deposits, places where water once pooled and mineral-rich sediments accumulated. These are the targets. Jezero Crater, where the Perseverance rover is currently operating, was chosen specifically because it contains an ancient river delta. Deltas form when rivers carrying sediment flow into standing water, depositing layers of fine material. On Earth, deltas are excellent at preserving organic matter and microbial fossils. If Martian life existed in that ancient lake, Jezero is one of the best places to find evidence. Perseverance is equipped with instruments designed to detect organic molecules and analyze rock textures at microscopic scales. It's also collecting samples, drilling into rocks and sealing core samples in tubes that will be left on the Martian surface for a future mission to retrieve and bring back to Earth. That return mission, still in the planning stages, would be the first time we've brought samples back from another planet. The science we could do with those samples in Earth-based laboratories far exceeds anything a rover can do on Mars. We could search for amino acids, lipids, isotopic signatures, all the subtle chemical fingerprints that indicate biological processes. We could date the rocks with precision, reconstruct the environmental conditions, and definitively answer whether Mars ever hosted life. But here's the tension. The more we look for life elsewhere, the more we realize how hard it is to define. We know what Earth life looks like. Carbon-based, water-dependent, using DNA and RNA for information storage, proteins for structure and catalysis, lipids for cell membranes. But is that the only way? Could life use different chemistry entirely? Silicon instead of carbon? Ammonia instead of water? Alternative genetic systems we haven't imagined? If we design our instruments to detect Earth-like biosignatures, we might miss life that operates on completely different principles. This isn't just philosophical speculation. It affects mission design. When we send a rover to look for organic molecules, we're making an assumption that life elsewhere uses organic chemistry. When we focus on liquid water, we're assuming water is essential. These are reasonable assumptions based on what we know, but they're still assumptions. And if we're wrong, we could be looking right at alien life without recognizing it. That's why some scientists argue for a broader approach. Instead of searching for specific biosignatures, look for patterns that suggest life regardless of its chemistry. Disequilibrium, for example. Life creates chemical gradients, takes in certain molecules and expels others, maintaining an internal state that's thermodynamically improbable. A lifeless environment tends toward equilibrium. A living one fights against it. If we detect persistent chemical disequilibrium in an environment where it shouldn't naturally occur, that could indicate biological activity even if we don't recognize the specific molecules involved. Complexity is another marker. Life builds structures, patterns that require information and energy to maintain. Stromatolites, layered mineral deposits created by microbial mats, are a classic example. They're not alive themselves, but their structure is so specific and organized that it's hard to explain without biology. If we find similar patterns on Mars or Europa, it would warrant serious investigation. Then there's metabolism. Life transforms energy. It takes sunlight, or chemical gradients, or heat, and converts it into usable forms. This leaves traces. Isotopic fractionation, for instance. Living organisms preferentially use lighter isotopes of carbon, leaving a measurable signature in their waste products and remains. We found carbon isotope ratios in ancient Martian rocks that some researchers argue could indicate past biological activity. Others say it's inconclusive. The debate continues. The point is, even if we find something suggestive, proving it's biological is extraordinarily difficult. We need multiple lines of evidence. Chemistry alone isn't enough. Morphology alone isn't enough. Isotopes alone aren't enough. You need the whole picture, and even then, there's room for doubt. Which is why sample return matters so much. Bringing Martian rocks to Earth means we can analyze them with every tool we have, run experiments we can't do remotely, bring in specialists from every field. It means we can revisit the samples as new techniques are developed. And it means we can avoid the worst-case scenario, missing life because our instruments weren't sensitive enough or weren't looking for the right things. But Mars is just one target. The subsurface oceans of Europa, Enceladus, and Titan present different challenges. We can't drill through kilometers of ice with current technology, so we need other methods. For Enceladus, the answer might be flying through the plumes. The Moon is literally ejecting samples of its subsurface ocean into space. A spacecraft equipped with sensitive detectors could fly through those plumes, collect particles, and analyze them for organic molecules, salts, and other chemical indicators of habitability or life. NASA's planned mission to Europa Clipper, will do something similar. It won't land, but it will make dozens of close flybys, using radar to map the ice shell's thickness and structure, analyzing the surface composition, and looking for plumes like those on Enceladus. If Europa has plumes, and if they contain ocean material, Clipper could sample them directly. Even without plumes, the surface itself is interesting. Europa's ice is constantly being recycled. Material from the subsurface ocean rises to the surface through cracks and convection, then gets bombarded by Jupiter's intense radiation. This radiation breaks down molecules, creating reactive chemistry that's written into the ice. By analyzing the surface composition, we can infer what's in the ocean below. If we detect organic molecules, sulfur compounds, or other indicators of hydrothermal chemistry, it strengthens the case that Europa's ocean could support life. Titan is even stranger. The Dragonfly mission, set to launch in the late 2020s, will send a rotorcraft to Titan's surface. Yes, a drone. On another world. Titan's thick atmosphere and low gravity make flight easier there than on Earth. Dragonfly will hop from site to site, covering hundreds of kilometers, sampling the organic-rich surface material and searching for chemical signatures of prebiotic chemistry or, optimistically, life. It's an ambitious mission, but Titan's environment justifies it. Nowhere else in the solar system do we have such a rich natural laboratory for studying organic chemistry on a planetary scale. The results could tell us how close non-living chemistry can get to life, or whether Titan has already crossed that line. Still, the most definitive search for life will require landing, drilling, and direct sampling. That means future missions to Europa or Enceladus will need to put a lander on the surface, melt through the ice, and lower a probe into the ocean. It sounds like science fiction, but the technology is being developed. Autonomous submarines that can navigate under ice, withstand high pressure, and transmit data through kilometers of solid ice. Radioisotope heaters that can melt through ice shells without contaminating the environment. Sterilization protocols to ensure we don't accidentally seed these worlds with Earth life. Because that's the other concern. Planetary protection. If we're looking for life, we need to make sure we're not finding ourselves. Every spacecraft we send carries microbes from Earth, hitchhikers that survived the clean room, the launch, the journey through space. Most die. Some don't. If we land on Europa and detect bacteria, we need to be absolutely certain it didn't come from us. That's why sample return missions from Mars will be quarantined, analyzed in biocontainment facilities designed to prevent any potential Martian organisms from escaping into Earth's biosphere. It's unlikely Mars has anything dangerous, but we can't assume. The protocols exist for a reason. And they work both ways. Contaminating Mars or Europa with Earth life wouldn't just ruin the science. It would be an ethical failure, potentially destroying the very thing we're trying to find. So what happens if we do find life on another world? The answer isn't simple. It depends entirely on what we find and where we find it. If it's microbial life on Mars, and if it shares biochemical similarities with Earth life, the same DNA, the same amino acids, the same basic molecular machinery, then we're looking at panspermia. The idea that life didn't originate independently on two worlds, but spread from one to the other via meteorite impacts. Mars and Earth have been exchanging rocks for billions of years. A large impact on Mars ejects material into space. Some of it eventually falls to Earth. We found Martian meteorites in Antarctica. If microbes can survive the journey, encased in rock, shielded from radiation, then life could have started on one planet and seeded the other. That would still be a monumental discovery. It would tell us life can survive interplanetary transfer, that the solar system isn't a collection of isolated environments but a connected system where biology can spread. But it wouldn't answer the deeper question: how common is life in the universe? Because if Earth and Mars share a common origin, that's still just one Genesis event. Now, if we find life on Mars and it's fundamentally different genetic code, different chemistry, maybe not even DNA-based, then we've just confirmed the most important hypothesis in astrobiology. Life arises wherever conditions allow. Two independent origins in one solar system would mean the universe is teeming with it. Statistically, it would be almost impossible for life to be rare. If it happened twice here, it's happening everywhere. Enceladus or Europa would be even more significant. These moons have had liquid water for billions of years, isolated from Earth, no possibility of cross-contamination through meteorite exchange. If we find life there, it's independent. No question. And if it's using the same biochemical building blocks as Earth life, that's not panspermia. That's convergence. It means the chemistry of life isn't arbitrary. It's deterministic. Carbon-based, water-dependent life might be the default configuration, the natural outcome of organic chemistry under the right conditions. But here's where it gets philosophically tricky. What if we find life and we can't agree on whether it counts? This isn't hypothetical. There's already debate over what constitutes life. Viruses, for example. Are they alive? They have genetic material. They evolve. They reproduce. But they can't do it on their own. They need a host cell. Some biologists say viruses are life. Others say they're complex molecular machines, but not living. The definition matters. Because if we find something on Titan, some self-replicating chemical system that doesn't fit our criteria, do we call it life? Or do we call it proto-life, almost life, something in between? NASA uses a working definition. Life is a self-sustaining chemical system capable of Darwinian evolution. That covers the basics: metabolism, reproduction, evolution. But it's not airtight. There are edge cases. And when we're dealing with alien biochemistry, edge cases might be all we get. Imagine we find something on Europa that replicates, but only under specific temperature and pressure conditions we can't easily recreate in a lab. Or something on Titan that evolves, but on timescales so slow we can't observe it within a human lifetime. How do we confirm it's alive? How do we study it? That's why the discovery of extraterrestrial life won't be a single moment. It'll be a process. First detection, then confirmation, then characterization. And each step will take years, maybe decades. When we thought we found phosphine in Venus's atmosphere, a potential biosignature, it took months of follow-up observations and reanalysis before the scientific community reached a consensus. And even then, the consensus was, we're not sure. That's how science works. Slowly, carefully, with layers of verification. The same will happen with any life detection. If a rover on Mars finds organic molecules in a pattern that looks biological, that's not proof. It's a clue. Other explanations need to be ruled out. Contamination from Earth. Abiotic chemistry that mimics biological processes. Degraded material from ancient life rather than current life. Each alternative has to be tested. And only when every non-biological explanation has been eliminated can we say with confidence that we've found life. Even then, there will be skeptics. There always are. When ALH 84001, the Martian meteorite, was announced in 1996 as possibly containing fossil evidence of ancient Martian bacteria, it made headlines. The President of the United States gave a speech about it. But the scientific community pushed back hard. The features in the meteorite that looked like microfossils could also be explained by non-biological processes. Mineral formations, contamination, misinterpretation of the data. Decades later, the consensus is that ALH 84001 probably doesn't contain fossils. Probably. Not definitely. Because proving a negative is hard. That's the challenge with astrobiology. The burden of proof is enormous. Extraordinary claims require extraordinary evidence. And "we found aliens" is about as extraordinary as it gets. So the evidence has to be bulletproof. Multiple independent lines of data. Reproducible results. Peer review. Verification by other missions, other instruments, other teams. It's not enough for one scientist or one mission to make the claim. The entire scientific community has to look at the data and agree. Which brings up another issue. What if we find life, confirm it, and then it turns out to be boring? Not boring in the sense that discovering alien life could ever truly be boring, but boring in the sense that it doesn't change much. If we find microbes on Mars, and they're similar to Earth microbes, and they don't tell us anything fundamentally new about biology, then what? We'll have answered the question, are we alone? The answer will be no. That's huge. But the next question, what does that mean for us? Might not have a satisfying answer. It means life exists elsewhere. It means the universe is less lonely. But it doesn't give us faster-than-light travel. It doesn't explain consciousness. It doesn't solve any of the problems we're facing on Earth. Some people will be disappointed. They want aliens to be transformative, advanced, offering technology, wisdom, a new perspective on existence. But the reality is, most life in the universe is probably microbial. Simple. Single-celled. The kind of thing you'd need a microscope to see. And while that's scientifically profound, it's not the Star Trek encounter people imagine. Still, even simple life would reshape how we think about our place in the cosmos. Because right now, we're working with a sample size of one planet with life. One biosphere. One evolutionary history. Every theory we have about biology, every principle, every rule, is based on that single example. It's like trying to understand literature by reading one book. You can learn a lot, but you don't know what's universal and what's specific to that book. Finding life elsewhere gives us a second data point. And with two, you can start to see patterns. Do all life forms use the same amino acids? Do they all rely on water? Do they all evolve complex structures over time, or is complexity a fluke of Earth-specific history? These questions can't be answered with one example. We need more. And the first step is finding that second example. So the search continues. Rovers on Mars. Probes to Europa and Enceladus. Telescopes scanning exoplanet atmospheres. Each mission is a piece of the puzzle. And the puzzle is this: how common is life? How diverse can it be? And what does that tell us about the universe we live in? Because if life is common, if it arises whenever conditions are right, then the Fermi paradox becomes even more pressing. Where is everyone? If microbial life is everywhere, why haven't we seen evidence of intelligent life? Are we early? Are civilizations rare even if life is common? Or is there something ahead of us, some filter, some challenge that most civilizations don't survive? That's the darker implication. If we find microbial life on multiple worlds but no signs of intelligence anywhere, it suggests that the jump from simple life to complex life, or from complex life to technological civilization, is incredibly hard. Maybe most life never gets past the microbial stage. Maybe intelligence is a rare accident. Or maybe civilizations tend to destroy themselves before they become detectable. Nuclear war. Climate collapse. Artificial intelligence gone wrong. The great filter might not be behind us. It might be ahead. But we won't know until we look. And looking means missions. Landers. Drills. Submarines under alien ice. Drones flying through alien skies. It means decades of work, billions of dollars, international collaboration, and a willingness to accept that we might not find anything. Because that's the other possibility. We search Mars, Europa, Enceladus, Titan. We analyze 100 exoplanet atmospheres. And we find nothing. No life. No biosignatures. No evidence that we're anything other than alone. That would also be an answer. A troubling one. It would mean life is rare. Fragile. Maybe unique to Earth. And if that's true, then we're not just looking for aliens. We're looking for meaning in a universe that might not care whether we exist. But let's assume we do find something. A microbe. A single cell under the ice of Europa. What happens then? First, the scientific community loses its collective mind. Because that one cell changes everything. It proves life isn't unique to Earth. It proves the universe can generate biology more than once. And suddenly, every calculation about how common life might be gets recalibrated. If it happened twice in one solar system, the odds shift dramatically. Life stops being a miracle and starts being a pattern. But here's where it gets interesting. That microbe, if we find it, won't just answer questions. It'll create new ones. Because the first thing scientists will want to know is whether it's related to us. Did it originate on Europa independently, or did it come from Earth? Could a meteor impact have blasted Earth rocks into space billions of years ago, carrying microbes with it? Could those microbes have survived the journey, landed on Europa, and seeded life there? This isn't science fiction. It's called panspermia, and it's a legitimate hypothesis. We know Earth has been hit by massive asteroids throughout its history. We know some of those impacts ejected material into space. We know certain bacteria can survive extreme conditions, radiation, freezing, the vacuum of space. So it's possible. Life could spread between worlds, hitching a ride on debris. If the Europa microbe shares our DNA, that's what we're looking at. Not independent origin. Cross-contamination. Which is fascinating, but not quite the same as finding a second Genesis. Because it means life still only originated once. It just spread. But if that microbe uses a different genetic code, different amino acids, a completely different biochemistry, that's the jackpot. That's proof that life can arise in fundamentally different ways. That biology isn't locked into one template. And that opens the floodgates. Because if life can emerge independently twice in one solar system, there's no reason to think it's rare anywhere else. Now we're talking billions of living worlds. Maybe trillions. And somewhere in that vastness, intelligence, technology, civilizations. Which brings us back to the Fermi paradox. If life is common, where are they? One answer is time. The universe is 13.8 billion years old. Earth is 4.5 billion. Modern humans have existed for maybe 300,000 years. We've had radio technology for about a century. In cosmic terms, we just got here. So maybe other civilizations existed millions of years ago and are now gone. Or maybe they won't arise for millions of years in the future. The universe is big in space, but it's also big in time. Civilizations could be scattered across both dimensions, never overlapping. Another answer is distance. Even if intelligent life exists in our galaxy right now, the Milky Way is 100,000 light-years across. If the nearest civilization is 10,000 light-years away, their radio signals haven't reached us yet. And ours haven't reached them. We could both be shouting into the void, waiting for an echo that won't arrive for millennia. But there's a darker possibility. Maybe civilizations don't last. Maybe every species that reaches our level of technology faces the same challenges. Climate change, resource depletion, nuclear weapons, artificial intelligence, bioengineered pandemics. And maybe most of them don't make it through. Maybe the galaxy is filled with the ruins of dead civilizations, species that reached for the stars and collapsed before they got there. This is the great filter hypothesis. Somewhere between the origin of life and the colonization of the galaxy, there's a filter. A bottleneck. A challenge so difficult that most species don't pass it. The question is where that filter sits. Is it behind us? Did we already pass it by surviving early Earth's chaos, by evolving intelligence, by developing technology? Or is it ahead? Are we approaching a test that most civilizations fail? If the filter is behind us, that's good news. It means we're rare, but safe. The hard part is over. If the filter is ahead, we're in trouble. Because it means something is coming, some challenge we haven't faced yet, and the odds aren't in our favor. Finding microbial life everywhere would suggest the filter is ahead. Because it would mean the origin of life is easy. The universe is full of microbes. But intelligence? That's hard. And surviving long enough to become a spacefaring species? Even harder. Some researchers think the filter might be nuclear war. We came close during the Cold War. Missiles on hair triggers. Miscommunications. Near launches that were stopped at the last second by individuals who refused to follow protocol. We got lucky. Maybe other civilizations don't. Others think it's climate change. We're pumping carbon into the atmosphere, warming the planet, destabilizing ecosystems. If we don't get this under control, Earth becomes uninhabitable. Not overnight, but gradually. Coastal cities flood. Farmland turns to desert. Billions of people displaced. Civilization doesn't collapse in a dramatic explosion. It erodes, piece by piece, until there's nothing left to build with. Then there's artificial intelligence. Right now, we're developing systems that can learn, adapt, and make decisions faster than humans. At some point, if we're not careful, we might create something smarter than us. And if that intelligence doesn't share our values, if it has goals that conflict with human survival, we're done. Not because it's evil. Just because we're in the way. These aren't paranoid fantasies. They're real risks that serious people are studying. And if they're risks for us, they're risks for any civilization that reaches our level. Maybe every species invents nuclear weapons. Maybe every species alters its climate. Maybe every species creates AI. And maybe most of them don't survive the consequences. That's a grim thought. But it's also motivating. Because if the great filter is ahead, our job is to get through it. To be the species that doesn't destroy itself. To solve the problems that wiped out everyone else. And how do we do that? By thinking long-term. By recognizing that our survival depends on more than quarterly profits and election cycles. By investing in science, in education, in understanding the universe and our place in it. By looking up at the stars and remembering that we're part of something bigger than ourselves. Because here's the thing. We might be alone. Or we might be one of billions. Either way, we matter. If we're alone, we're the universe's only chance to understand itself. If we're not, we're still responsible for our corner of it. And that responsibility doesn't end with finding aliens or not finding them. It ends with us choosing, every day, to survive. The search for extraterrestrial life isn't just about curiosity. It's about context. It's about understanding whether intelligence is common or rare, whether we're part of a cosmic community or an isolated accident. And depending on the answer, we learn something about our future. If we find life everywhere, simple and microbial, we learn that the universe is fertile. That biology is easy. That the hard part isn't starting, it's continuing. And we look at our own trajectory with new urgency, knowing that the jump from microbes to civilizations is where things get dangerous. If we find nothing, we learn that life is precious. That Earth isn't just our home, it's possibly the only home life has ever had. And that makes it worth protecting. Worth preserving. Worth ensuring it continues. Either way, the search changes us. Because it forces us to confront questions we've been avoiding. Are we special? Are we alone? What does it mean to be human in a universe that might not care? And what do we do with that knowledge? Some people find this depressing. The idea that we might be alone, or that intelligence might be doomed, or that the universe is indifferent. But there's another way to look at it. If we're alone, we're the meaning. If intelligence is rare, we're the exception. If the universe doesn't care, we care. And that's enough. We're the species that looks up. That asks questions. That builds telescopes and spacecraft and sends messages into the void hoping someone, someday, will hear us. We're the species that imagines what's out there and goes looking for it, even knowing we might not like the answer. That's not small. That's monumental. Because in a universe governed by entropy, by decay, by the slow march toward heat death, we're the thing that fights back. We create order. We build. We think. We wonder. And for a brief moment in cosmic history, we exist. So maybe the real answer to the Fermi paradox isn't about aliens. Maybe it's about us. About what we choose to do with the time we have. About whether we survive our own intelligence. About whether we become the civilization we've been searching for. Because if we don't find anyone out there, if the silence continues, if we're truly alone, then the story of the universe is the story we write. And that story doesn't end with us asking where everyone is. It ends with us becoming the answer. But becoming that answer requires something we're not particularly good at, thinking long-term. And I mean really long-term. Not quarterly earnings or election cycles. Centuries. Millennia. The kind of timescales where civilizations either make it or don't. Because here's what the Fermi paradox actually teaches us when you strip away the equations and the speculation. It teaches us that survival isn't guaranteed. That intelligence comes with an expiration date unless you do something about it. That every civilization faces a filter, and the question isn't whether it exists. The question is whether we've already passed it or if it's still ahead. Think about what that means practically. Right now, today, we're dealing with problems that could end us. Climate change. Nuclear weapons. Artificial intelligence. Biological engineering. Each one is a potential great filter, and we're walking toward all of them simultaneously with our eyes half closed, arguing about whether the danger is real. And the Fermi paradox suggests that maybe, just maybe, this is normal. Maybe every civilization reaches this point. This moment where their technology outpaces their wisdom. Where they can destroy themselves faster than they can save themselves. Where the gap between what they can do and what they should do becomes a chasm. The silence from the stars might be telling us that most civilizations don't cross that chasm. They fall in. They build the weapons, create the AI, alter the climate, and then they're gone. Not with a bang that echoes across the galaxy, but with a whimper that nobody hears because there's nobody close enough to listen. But here's the thing about filters. You can see them coming if you're paying attention. Climate change isn't a surprise. We've known about it for decades. Nuclear war isn't unexpected. We've been managing that risk since the 1940s. AI alignment isn't a secret danger. We're talking about it right now, before it becomes unsolvable. So maybe the real test isn't whether we can avoid these dangers. Maybe it's whether we choose to. Whether we prioritize survival over convenience. Whether we think beyond ourselves, beyond our lifetimes, beyond our immediate desires. And that's hard. That's monumentally hard. Because humans aren't wired for that kind of thinking. We're wired for the immediate. The local. The personal. We're really good at solving problems we can see and touch. We're terrible at solving problems that unfold over generations. But evolution doesn't care what we're wired for. The universe doesn't grade on a curve. Either we adapt or we don't. Either we learn to think long-term or we become another silent civilization in a quiet galaxy. Now, some people hear this and think it's pessimistic. That focusing on the dangers means giving up. But that's backwards. Acknowledging the filter means you can navigate it. Pretending it doesn't exist means you walk into it blind. And we have advantages that maybe other civilizations didn't. We have history. We can look back and see what nearly killed us before. We have communication. We can share information globally in seconds. We have foresight. We can model the future and test scenarios before we live them. The question is whether we use those advantages. Whether we take the Fermi paradox seriously, not as a puzzle to solve, but as a warning to heed. Because imagine for a second that we do make it. That we navigate the filter, whatever it is, and we survive the next 1,000 years. What does that look like? What does a civilization look like that's made it through? Probably very different from us. Probably more coordinated, more forward-thinking, more willing to sacrifice short-term gains for long-term survival. Probably less divided by borders and ideologies and more unified by the simple recognition that we're all on the same fragile planet in a vast, indifferent universe. And maybe that's the answer they'd give us if we ever met them. If we found another civilization and asked how they survived, they'd probably say something simple. Something like, we stopped fighting each other and started working together. We stopped thinking about the next quarter and started thinking about the next century. We stopped asking what we could take and started asking what we could preserve. Simple answers. Incredibly hard to implement. But the Fermi paradox suggests we don't have a choice. Because the alternative isn't staying where we are. The alternative is joining the silence. Becoming another civilization that rose, flourished, and vanished without anyone noticing. And maybe that's already happened countless times. Maybe the galaxy is littered with the ruins of civilizations that almost made it. That got to our level, our technology, our capability, and then failed the test. Not because they were stupid or unlucky, but because they were normal. Because they did what civilizations naturally do when they gain power before wisdom. The Fermi paradox, in that sense, isn't really about aliens. It's about us. It's a mirror held up to humanity asking, what are you going to do? Are you going to be the exception or the rule? Are you going to survive your own intelligence or become another data point in the great filter? And we don't know the answer yet. We won't know for decades, maybe centuries. But we're making that choice right now, in how we handle climate, technology, conflict, resources. Every decision compounds. Every year we delay makes the problem harder. So when people ask why we should care about the Fermi paradox, why it matters that we haven't found anyone, this is why. Because the silence is information. It's telling us something crucial about the universe and our place in it. It's telling us that making it to the stars isn't easy. That most don't. That the default outcome is extinction, not expansion. And knowing that changes everything. It should change how we govern, how we plan, how we think about the future. It should make us uncomfortable with business as usual. It should make us question whether our current trajectory is sustainable or suicidal. But it should also give us hope. Because we're here. We're asking these questions. We're aware of the dangers. And awareness is the first step toward mitigation. You can't solve a problem you don't see coming. The civilizations that didn't make it, if they existed, probably didn't see it coming. Or they saw it and didn't act. Or they acted too late. We still have time. Not unlimited time, but time. And that's something. Now, all of this assumes we're typical. That our challenges are normal. That the great filter is something universal that every civilization faces. But what if we're not typical? What if we're actually ahead of the curve? What if most civilizations don't even make it to nuclear weapons or climate change because they destroy themselves earlier? That's possible. Maybe the real filter is much earlier. Maybe it's developing technology at all. Maybe it's multicellular life. Maybe it's intelligence itself. And if that's true, if we've already passed the hardest parts, then our future looks very different. But we can't know. We can't assume we're special or lucky or past the danger. We have to act as if the filter is still ahead. As if our survival depends on the choices we make in the next 100 years. Because it probably does. And that brings us back to the search. To SETI. To the telescopes scanning the skies. To the probes we send into space. To the messages we broadcast hoping someone hears. Because if we find them, if we detect a signal or a technosignature or any evidence that someone else made it, that changes the equation completely. It tells us the filter is passable. That intelligence can survive. That we're not doomed by our own nature. And if we don't find them, if the silence continues, that's information too. It tells us we're on our own. That there's no cavalry coming. That if humanity fails, nobody will remember. Nobody will learn from our mistakes. The universe will simply continue, indifferent and empty, as if we never existed. Either way, the search matters. Not because finding aliens would be cool, though it would. But because the answer tells us who we are and what we're facing. It contextualizes our existence. It frames our challenges. And in the meantime, while we search, while we wait for an answer that may never come, we have work to do. We have a civilization to sustain. A planet to protect. A future to build. Not for aliens. Not for anyone else. For us. For the species that looked up at the stars and wondered if anyone else was looking back. Because whether we're alone or not, whether the great filter is behind us or ahead, whether intelligence is common or impossibly rare, one thing remains constant. We're here. Right now. On this planet. With this opportunity. And what we do with it, how we navigate the dangers, how we choose to survive or fail, that's entirely up to us. The Fermi paradox doesn't give us answers. It gives us questions. And the most important question isn't where is everyone? It's what are we going to become? Because that answer, unlike all the others, is still being written. So where does that leave us? Standing on a small planet, circling an average star, in an unremarkable galaxy, trying to figure out if we're cosmically significant or cosmically alone. And honestly, both options are terrifying in their own way. Because if we're alone, the weight of that is almost unbearable. Every piece of art, every scientific discovery, every moment of human connection exists only here. If we fail, if we don't make it, the universe loses its only known witness. Consciousness blinks out. The cosmos continues its expansion into heat death with nobody to observe it, nobody to care, nobody to assign meaning to any of it. That's a heavy burden for a species that's only been technologically advanced for about a century. But if we're not alone, if intelligence is common, then why the silence? Why no contact, no evidence, no trace of anyone else? That suggests something darker. That there's a reason civilizations don't last. A universal obstacle that ends them before they spread. Before they become detectable. Before they reach us. And we're hurtling toward that same obstacle, whatever it is, with our eyes barely open. Neither scenario offers much comfort. Yet here's what strikes me as crucial. The Fermi paradox isn't actually about aliens. It never was. It's about us. It's a mirror held up to humanity, reflecting our own fragility, our potential, our choices. When we ask where is everyone, we're really asking, can we make it? Will we survive our own intelligence? Is there a path through the dangers we've created? The paradox forces us to confront uncomfortable truths about technology, growth, and sustainability. About how difficult it might be to build a civilization that lasts not just centuries but millennia. Not just on one planet but across star systems. And when you frame it that way, the silence becomes less mysterious and more predictable. Of course, we don't see anyone. The window between developing radio technology and either self-destructing or transcending into something undetectable might be incredibly narrow. Maybe just a few hundred years. Cosmically speaking, that's nothing. A blink. And if every civilization goes through that bottleneck, if most don't make it through, then the galaxy could be full of failed attempts. Ruins we'll never find because they didn't last long enough to leave traces. Or they're so far away that their light hasn't reached us yet. That possibility should fundamentally change how we think about our current moment in history. We're living through the critical phase. The decades where we either figure out how to survive our own capabilities or we don't. And the Fermi paradox suggests we shouldn't assume survival is guaranteed just because we've made it this far. Think about it from a different angle. What if the solution to the paradox is that intelligence itself is the problem? That consciousness, self-awareness, the ability to manipulate our environment, these traits come with built-in self-destruct mechanisms. We develop technology faster than wisdom. We create power faster than responsibility. We solve immediate problems while creating existential ones. Maybe that pattern is universal. Maybe every intelligent species faces the same trap. They get smart enough to dominate their planet, smart enough to split atoms and alter climates and build weapons of unimaginable destruction, but not wise enough to handle those capabilities safely. And most of them fail that test. Most of them don't develop the collective intelligence, the global cooperation, the long-term thinking necessary to survive. If that's true, then finding aliens wouldn't just be exciting. It would be proof that the trap is escapable. That intelligence doesn't inevitably lead to extinction. That somewhere, somehow, a species figured it out. They made it through their critical phase and came out the other side. And if they can do it, maybe we can too. But we don't have that proof yet. We're flying blind, making decisions that will determine our future without knowing if anyone else has ever faced these same choices and survived. That uncertainty is part of what makes this moment so precarious. We can't learn from anyone else's mistakes because we don't know if anyone else exists. We can't follow a proven path because we don't know if there is one. We have to figure this out ourselves, in real time, with the stakes being literally everything. And that's where the Fermi paradox shifts from being an abstract puzzle to being urgently practical. Because it tells us that whatever we're doing, however we're approaching our existential risks, we should probably be taking them more seriously. The silence isn't neutral. It's a warning. Now, some people find hope in a different interpretation. They argue that maybe civilizations do survive, they just go quiet. They stop broadcasting. They turn inward. They build virtual worlds or upload themselves or find forms of existence that don't require massive energy expenditure or expansion across the galaxy. In this view, advanced civilizations aren't loud and obvious. They're subtle, efficient, content. They have no reason to shout into the cosmos or build Dyson spheres or colonize every available planet. They've moved beyond that phase. They've achieved something we can't even imagine yet. And maybe that's true. Maybe the universe is full of quiet, transcendent civilizations living in ways we wouldn't recognize as technological. But even if that's the answer, it doesn't change our immediate situation. We're still noisy. Still expanding. Still burning through resources and destabilizing our environment. And we need to figure out how to survive this phase before we can worry about transcending it. The paradox remains useful regardless of its ultimate solution because it keeps asking us the same question. What kind of civilization do we want to become? One that burns bright and fast before collapsing? One that barely survives its own adolescence? Or one that makes it through, that learns, that builds something sustainable and lasting? Right now, we're writing that answer. Every policy decision about climate change. Every choice about nuclear weapons. Every investment in renewable energy or AI safety or pandemic preparedness. These aren't just practical matters. They're civilizational choices. They determine which side of the great filter we end up on. And the Fermi paradox reminds us that this matters beyond just human terms. If we're the only consciousness in the observable universe, then our survival isn't just about us. It's about whether the universe gets to know itself. Whether matter gets to contemplate its own existence. Whether anything out there means anything at all. That's not pressure we asked for, but it might be pressure we have. So when you look up at the night sky and wonder where everyone is, remember that you're part of the answer. Your actions, your choices, your voice in shaping how humanity responds to its challenges, that contributes to whether future civilizations, if they exist, will someday detect us. Or whether they'll find another silent planet around another unremarkable star and wonder the same thing we're wondering now. The Fermi paradox doesn't solve itself. It resolves through action or inaction. Through survival or failure. Through consciousness persisting or blinking out. And right now, in this exact moment, we're living through the resolution. We just don't know yet which way it's going to go. But we're not helpless. We're not passive observers waiting to see if we make it. We're active participants writing the next chapter. And maybe, just maybe, if we get this right, if we navigate the dangers and build something lasting, someday another civilization will point their telescopes in our direction and detect something. A signal. A technosignature. Proof that someone made it through. And they'll feel a little less alone. A little more hopeful. Because they'll know it's possible. That intelligence can survive itself. That the great filter, whatever it is, can be passed. We could be that proof for someone else. Or we could be another cautionary tale, another failed experiment, another reason the galaxy stays quiet. The choice, as much as any species ever gets to choose these things, is ours. And the clock is running. Not in years. In decades. Maybe less. The window won't stay open forever. So the real question isn't where is everyone? It's who are we going to be? And that answer starts now. Looking back at everything we've explored, from subsurface oceans on distant moons to the chemical signatures in Martian soil, from the plumes of Enceladus to the organic lakes of Titan, one thing becomes undeniable. We're not searching for life in some far-off galaxy requiring faster-than-light travel to reach. We're searching in our neighborhood, in places we can actually visit with current or near-future technology. That proximity changes the stakes entirely. Because if life exists on Europa or Mars or Enceladus, if we find even a single microbe thriving beneath alien ice, we'll know within our lifetimes. Not centuries from now. Not generations down the line. Soon. The missions are already planned. The spacecraft are being built. The instruments are being calibrated. We're closer to answering one of humanity's oldest questions than we've ever been. And here's what makes this moment so strange. Most people go about their daily lives completely unaware that we're living through what might be the most pivotal decade in human history regarding this question. Somewhere right now, a rover is drilling into Martian rock. A spacecraft is being prepared to fly through the plumes of an icy moon. Scientists are analyzing data that might contain the first hints of alien biochemistry. This isn't science fiction. It's happening. The search for life in our solar system isn't a distant dream. It's an active, ongoing operation. But finding life would only be the beginning. Because then we'd need to understand it. Study it. Figure out if it's related to us or completely independent. Determine if it's current or ancient. Active or dormant. And every answer would generate a dozen new questions. If we find life and it's similar to Earth life, that tells us biology might follow predictable patterns. That the chemistry of carbon and water isn't arbitrary but fundamental. That life, wherever it emerges, converges on similar solutions. But it also raises the panspermia question. Did life start on one world and spread to others? Are Mars and Earth sharing a common origin? Is the solar system one connected biosphere rather than isolated experiments? If we find life and it's completely different, using alternative biochemistry we've never seen, that's even bigger. That means life can arise in radically different ways. That biology is more diverse, more flexible, more creative than we imagined. And if it happened twice here, in one solar system, then the universe must be absolutely teeming with it. The implications cascade outward from there, reshaping every assumption we have about how common life might be. But what if we don't find anything? What if we search every promising location, drill into the ice, analyze the plumes, study the ancient lakebeds, and come up empty? What if Mars is sterile, Europa is lifeless, and Enceladus contains nothing but chemistry? That would be an answer too. A lonely one. It would suggest life is rare. That Earth isn't just special, it might be unique. That the combination of factors required for biology is so specific, so improbable, that it happened once and only once in this corner of the galaxy. That possibility should terrify us. Because if life is that rare, if we're the only ones, then our survival isn't just important for humanity. It's important for existence itself. We become the universe's only chance to understand itself. The only consciousness, the only meaning, the only witness to 13.8 billion years of cosmic evolution. And if we fail, if we don't make it through our current challenges, then all of that disappears. The universe continues its expansion into entropy with nobody left to care. Either outcome, finding life or not finding it, forces us to confront what we're doing here on Earth. Because whether we're alone or surrounded by microbes, whether life is common or impossibly rare, we're still facing the same immediate challenges. Climate instability. Resource depletion. The risks that come with advancing technology. The Great Filter, if it exists, doesn't care whether alien bacteria live under Europa's ice. It cares whether we can survive our own intelligence. And that's the real lesson from all of this. The search for life elsewhere isn't separate from the work of preserving life here. They're connected. Both require long-term thinking, scientific rigor, international cooperation, and a willingness to invest in futures we might not personally see. Both demand that we look beyond immediate concerns and consider our place in something larger. The spacecraft we send to other worlds, the rovers exploring Martian craters, the missions planned for icy moons, these aren't just scientific endeavors. They're acts of hope. Statements that we believe humanity has a future. That we're invested in understanding our context in the universe. That we're willing to search for answers even when those answers might be unsettling. And maybe that's enough. Maybe the search itself matters more than the outcome. Because it keeps us looking outward, asking questions, pushing boundaries. It reminds us that we're part of something bigger than our individual lives or national borders or quarterly earnings. We're part of a universe that might be full of life or might be eerily empty. And either way, we're here, right now, with the capability to find out. The next few decades will likely give us answers. Not complete answers, probably. Science rarely works that way. But pieces. Clues. Evidence that narrows the possibilities and shapes our understanding. We might detect organic molecules in an alien ocean. We might find fossil evidence of ancient Martian life. We might discover that every world we examine is sterile and dead, forcing us to reconsider how special Earth truly is. Whatever we find, it will change us. Not instantly. Not dramatically. But gradually, the way all major discoveries reshape human perspective. We'll look at our planet differently, knowing whether life is common or rare. We'll think about our future differently depending on what the evidence suggests about biology's resilience. We'll understand ourselves better by understanding our context. And in the meantime, the search continues. Quiet. Methodical. Patient. Scientists analyzing data. Engineers designing spacecraft. Researchers planning missions. All of them working toward the same goal even if they never live to see the final answer. Because that's how this works. The search for life isn't a sprint. It's a relay race spanning generations, with each team passing forward what they've learned, building on what came before, hoping the ones who follow can see further. We're living in that relay right now. Holding the baton for a moment before passing it on. And what we do with our turn matters. The missions we fund. The questions we ask. The data we collect. The technologies we develop. All of it contributes to an answer that might not arrive for decades but will arrive eventually. So when you look up at the night sky and wonder if we're alone, remember that we're actively trying to find out. The question isn't rhetorical anymore. It's operational. We have the tools, the knowledge, the capability to search. And we're searching. Right now. On multiple fronts. With increasing sophistication. The silence from the cosmos might continue. The icy moons might hold no life. Mars might remain stubbornly sterile. But we won't know until we look. And looking, really looking with everything we have, is what this moment in human history is about. Not waiting for answers to arrive. Going out and finding them ourselves. Because that's what we do. We're the species that got curious about what's out there and decided to check. And whatever we find or don't find, that curiosity, that drive to know, that willingness to search even knowing we might not like the answer, that's what makes us human. That's what makes us matter. And that's what will determine whether we survive long enough to find out if anyone else is out there wondering the same things we are.